Hi there, and welcome to today's Lightning Talks. I'm Samantha Kim, and I'm part of the marketing team here at Solo.io. I'm excited to welcome our Lightning Talk speakers today, so please help me extend a warm welcome to Kasun and Marino, who will be sharing information about IPv6 and service mesh. Kasun and Marino, over to you.
Sorry about that. Welcome to the session titled Multi-Cluster Communications with IPv6. Hope you guys have been enjoying SoloCon so far. So my name is Kasun. I'm a field engineer at Solo in the APAC team based out of New Zealand. And with me is my colleague, Marino. Marino, do you want to say a few words?
Sure. Hey, everyone. My name is Marino Wijay. I'm a developer advocate at Solo up in North America. And I'm here to talk to you about IPv6 and service mesh. So looking forward to it, and welcome to SoloCon, everyone.
So before we talk about some of the challenges in today's internet, let's take a step back and look at how the internet protocol has evolved. I'm sure everyone has heard of what the internet protocol is. It's just the main set of rules that govern the exchange or transmission of data between devices on separate networks. The first non-experimental version of the Internet Protocol, version 4, or IPv4 as we call it, has been the cornerstone of the internet since its inception. When the specification was first publicized, nobody really envisioned the increasing amount of devices and services communicating over the internet. There's massive amounts of traffic over the internet due to this. And that's specifically due to, or especially due to technologies such as IoTs, 5G. There's even 6G coming out in the future. There are other challenges, such as IP mobility. When devices move between networks, having to maintain a constant or permanent IP address, inefficiencies in address allocation, in other words, inefficient IP distribution when organizations had an oversupply of IP addresses. And then there's security implications, such as addresses being easily discoverable. And there's much more challenges that we're facing today. Next slide, please, Mary. So to meet the challenges and demands, this constantly ever-growing internet required a new protocol. And that came out in the form of IPv6 or version 6. IPv6 was launched to the public in 2012 as the standard that could eventually replace IPv4. And IPv6 addresses are 128 bits. But if we talk about the IPv4 side of things, then IPv4 has 32 bits. Sorry, I think Marina, I think we may have gone up the slide. Wait, sorry. So IPv4 has 32 bits of addresses, which means that it only allows about 4.3 billion unique addresses. So there's obvious issues with that. So if you move to the next slide, thank you. So what's the catch, you ask, right? Why hasn't it kind of taken off, similar to IPv4? So if you look at these Google trend graphs, the IPv6 adoption has been quite slow. And that's largely due to people being reluctant to migrate across to IPv6. There's obvious compatibility issues with IPv4 and IPv6. So if you take a IPv6 workload, they may not be able to talk to IPv6 only workload. You need some sort of netting or translation in between to be able to do that. And some people don't even understand enough about IPv6. It's just that complex compared to IPv4. And then having to remember the IPv6 address. Remember, it's 128 bits long, right? So it's just really difficult to remember as well. So for that reason, IPv4 and IPv6 will coexist, and it will exist for some time. So if you move to the next slide, please. So in Kubernetes, IPv6 has been introduced in a couple of modes. It has been released as a single stack mode that's been out since 1.1.18 in beta. And it's also been released as dual stack mode. And it's been out since 1.2.1, and it actually has gone GA quite recently in 1.2.3. So what do these actually mean? So single stack means that it's a single interface, a single IP for your workloads, whereas in dual stack, it's actually multiple different IPs, IPv4 IP and then IPv6 IP. Now, if there are some factors that may or may not allow IPv6 workloads in the cluster. You need to make sure the cloud vendor support exists in the underlying infrastructure. AWS is one of the first cloud vendors to introduce IPv6 and a set of APIs around that. And also in Kubernetes, there's what's called the cloud, the container network interface, or the CNI. It's actually the underlying network layer in Kubernetes, and so that needs to support IPv6 as well. Regardless of whether it's single or dual stack, there are popular CNIs like Calico and Cilium that supports IPv6. And so, before I hand over to Marino, I just also want to reiterate that you need, when you're planning to run workloads, IPv6 workloads, you need to make sure the cloud vendor support is there, and also really think about whether you want single stack compatibility or dual stack compatibility, because in the case of single stack, you may have some challenges talking to IPv4 workloads, either internally or externally. So the recommendation there is obviously to go with dual stack, and that this is one of the reasons why in Kubernetes it has been introduced. So over to Marino to talk about service meshes.
Yeah, thanks, Kasun. So when considering a service mesh or using a service mesh, the underlying Kubernetes cluster needs to support IPv6. And as Kasun already mentioned, as of Kubernetes 1.2.3, IPv6 and even IPv4 dual stack is a stable feature. So consider when provisioning services for deployments in your cluster, if you aren't using a service mesh, then you would normally need to expose your services as normal. But if you're using something like dual stack, then you just need to specify this as a flag in your services configuration. Now, in the case of using a service mesh, the ingress gateway object will need to ensure its service IP is using the necessary stack. So whether we want v4 or v6, we just go ahead and specify that. But realize a lot of these requirements actually happen at layer 3. We are simply telling Kubernetes to just honor the v6 addresses we would consume at the service level. Furthermore, because pods are on an IPv6 enabled network, they have no issues communicating with that ingress gateway and anything beyond it. The last remaining piece we need to consider is actually DNS and the quad A records, or the AAAA records. Take for a moment here that when we're actually creating a DNS record, the difference between IPv4 and IPv6 doesn't change. So the operation for creating a quad A record doesn't deviate from that of an A record. AAA just maps to an IPv6 address. When this is in place, it becomes quite straightforward to proceed to deploy a service mesh with IPv6. With service mesh, you can go ahead and deploy the control plane, which if you're using Istio, would be Istio-D and proceed to deploy, let's say, an ingress gateway resource that handles incoming HTTP requests. Nothing changes from an operational point of view, as the service mesh provides the necessary abstractions to allow for less concern around the underlying IP stack or the TCP IP stack. Now let's take a look at Glue Mesh and how this doesn't really change even if we're using v6. So Glue Mesh, it aims to simplify the configurations of things like your security policies and traffic management, while also providing additional extensibility to the actual Envoy proxy, that sidecar that sits alongside your main containers and your pods. The Glue Mesh management plane itself sits in a Kubernetes cluster, which actually doesn't participate in the service mesh. However, it does control Glue Mesh, and it controls all of the clusters that are running Istio and the Glue Mesh agent. These are our workload clusters where our services and our pods live. As long as the Glue Mesh management plane itself has IPv6 reachability to the workload clusters, those ones running Kubernetes and Istio, this enables the controlling of these workloads along with pushing things like policies for like traffic management or even security policies. When considering security and working to create, let's say, like an authorization or RBAC policy, Glue Mesh access policies can streamline these configurations. If we attempt to route to various services or endpoints inside of our clusters, virtual services, destination rules, and service entries normally would be deployed, except we can simplify this using a route table resource in Glue Mesh. If you think about it, nothing here has to do with IPv6 or even IPv4. We are working on an abstraction on top of Istio to just streamline those configs, but IPv6 just works. That being said, inbound communications should continue to function provided that you have DNS set up correctly. So in a nutshell, like IPv6 is there, Glue Mesh is there, Istio is present, but at the end of the day, whether you had IPv4 or IPv6 as a stack doesn't really matter. So to wrap up, IPv6, despite being sidelined by NAT technologies for so many years, has many use cases, with many cloud providers natively supporting IPv6 in their core networks. There is even stateful support or full stable support for this inside of Kubernetes as 1.23. And while Istio provides a powerful service mesh that gives us traffic management, observability, and even security capabilities, we can leverage Glue Mesh to streamline these configurations to simplify how we go about running service mesh with IPv6. We hope you enjoyed this lightning talk. Thank you very much.